Okay, so the first thing I want to do now is to prove Van Kampen's theorem. So recall that the setup, we have a simplicial complex, which is a union of two subcomplexes. We have some base point in the intersection. We consider these maps. We have a map from the edge group of the intersection to the edge group of the individual pieces. These maps are called J1 and J2. And Van Kampen says if the intersection is connected, then the edge group of K is isomorphic to the free product of edge groups of K1 and K2, quotiented by the normal subgroup, which I'm writing double brackets for, generated by J1 E epsilon, J2 epsilon inverse for epsilon in the edge group of the intersection. Okay, so the way you should think about this is, well, we know how to write down a presentation for these edge groups. And a presentation for the edge group of the free product is just built out of presentations for these individual groups. And this is saying that to get a presentation for the edge group of the full complex, you just need to add some additional relations, that each of these things is equal to 1. So as an example, let me explain how to compute the fundamental group of the torus in this way. And I'm going to do this a little bit more on the topological side. So we're eventually going to prove, and we're moving towards that this week, that these edge groups are the same as the fundamental group of the geometric realization. So that gives you a direct translation of this Van Kampen theorem into a statement about fundamental groups of spaces. And so let me explain what that says in like this example. So I'm going to take the torus, described like this as usual, and let me take so I want to decompose this into two pieces. So one is going to be like this bit here on the inside, this disk, and then the rest is going to be in the other piece. And these overlap in this circle on the boundary. Oops. Right, so let's say this is K1, this is K2, and the blue is the intersection. So K1, okay, and I'm working topologically, so yeah, maybe I should better call them A, B, and A intersect B. There's A, B, and A intersect B. And right, so B is topologically a closed disk. A intersect B is topologically a circle, and A is topologically a torus without a disk. And well, up to homotopy, this is a wedge of two circles, which we've seen before. A torus with one boundary component is homotopy equivalent to a wedge of two circles sitting inside. And just draw it like this. And okay, so now what does Van Kampen say in this situation? So Van Kampen says the fundamental group of the torus is the free product of the fundamental group of A with the fundamental group of B with some quotient. So you're supposed to look at, right, so you have the fundamental group of the intersection. So in this case, the fundamental group of the intersection is Z, and it's, well, yeah, so now we should give these things some names. So let's see, the fundamental group of A, this is a free product of Z with itself, since that's the fundamental group of this wedge. And let's give the generators names. Let's say like X and Y, maybe, which are like X and Y in this picture, or I guess on the torus, we could call this like X and Y. There's a slight problem if I do that because of the base points. I want this to be the base point P, but the base point has to contain this complex. So maybe I make this go into the base point, keeping it to be a disk and keeping the intersection to be a circle. Anyway, right, so then the generator of the intersection, this circle, well, this circle that in A, how does it look? So let me call that epsilon. It's generated by epsilon. So the map from pi1 of A intersect B to pi1 of A is sends epsilon to, well, epsilon is just this blue circle. And in the fundamental group of the torus without a boundary component, that just goes around X, Y, X inverse, Y inverse. And well, we also know that the fundamental group of A intersect B to the fundamental group of B, this sends epsilon to the identity, since the fundamental group of B is trivial. So the quotient that we have here is, so this I'm describing here, J1 and J2, we're supposed to quotient by the subgroup that says J1 of epsilon, J2 of epsilon inverse is, the subgroup generated by these elements. It's enough to just do it, for this one epsilon, since epsilon generates this Z. So this is the description you get, but J2 of epsilon, as we just said, is the identity element, and J1 is this word, X, Y, X inverse, Y inverse. So the upshot of this is, so this group is trivial. This group is generated by X and Y. So we see here what we conclude. Maybe I'll write it at the top. So then pi1 of the torus, it has this presentation with generators X and Y and a single relation, X, Y, X inverse, Y inverse is 1. And well, that's a presentation for a free abelian group of rank 2. Okay, so Van Kampen's theorem can be a little bit tricky. There's a decent amount of algebra going on here. This would be it would be great if you could ask questions now, but if this is confusing, parts of this are confusing, please just ask in Piazza or in office hours. All right, so now I want to turn towards the proof of Van Kampen's theorem. And before we do that, we need to recall the presentation that we described for an edge group. And this was the group that we called, well, we wrote this as GLT. So let's choose, so we choose T in L, a maximal tree. And then we have this presentation. So ELP is isomorphic to the group with generators Gij for whenever Vi and Vj span a simplex of L. So those are the generators, one for every edge of the simplicial complex. And then there are relations. So Gij is trivial if Vi and Vj are an edge in the maximal tree, or are a simplex, span a simplex in the maximal tree. It might be an edge, this Vi might be equal to Vj, that might just be a vertex. And then we have relations, another relation, Gij, Gjk is Gik, whenever this triple, Vi, Vj, Vk, is a simplex of L. Oh, right. And I guess I should have said, so whoops. I should have said that we write V1 through V whatever D for the vertices of L. So that's the Vi and Vj's that are appearing here. Okay. So now let's do the proof of Van Kampen. And the proof is rather simple. What we'll do is we compare presentations for the edge groups with L, K, K1, K2 and K1 intersect K2. The only thing we need to do is to choose the maximal trees for, so right, the presentation requires a choice of the maximal tree. And we want to choose the tree in a compatible way, which will make it clear how these groups are related, the presentations are related. So to start, let's choose a maximal tree, T12 in the intersection, K1 intersect K2. And well, we can extend to a maximal trees T1 in K and K1 and T2 in K2. I mean, all I'm saying here is T12 is also a tree in K1. It's probably not maximal, but we can always extend it to a maximal tree just by adding more edges. And then set T to be T1 union T2. So observe that T is a maximal tree of K. Well, yeah, so it's a general fact that if you have two trees, T1 and T2, and you glue them along a tree, T1, 2, then the result is a tree. And it's going to be maximal because each of T1 and T2 is maximal. So I'm not going to write down all the details, but let me just draw a picture to try to convince you that the union of two trees glued along a tree is a tree. So here's a tree. Let's say this is our T1, and let's now pick a T2, which might overlap with T1, but it does so in a tree. And then it goes off and does its own thing. So the intersection of these two is this red bit here. So here's, yeah, so this is T2, and then T1, 2 is the red bit. And, well, okay, I mean, okay, so here, I mean, I don't know how convincing this is. This is proof by picture. This isn't a proof at all, really. It's just an illustration. If you glue two trees along a tree, then the result is also a tree. But you could prove this without too much trouble. You prove that the result doesn't have any backtracking using the fact, or this union doesn't have any backtracking, non-backtracking loops, using the fact that T1 and T2 don't. And the intersection also doesn't. Okay. Right, so given this, now we just want to write down the presentations. So we have, let's first write down a presentation for K. No, let me start with K1. So, right, I mean, I wrote this down before. So we have generators Aij, where Vi, Vj is in K1. And then we have relations, Aij is 1, or Aij AJK is AIK. When here this is VI, VJ is in K1. And here we have VI, VJ, VK. This is a simplex in, no, this is K1 and this should be T1 here. And maybe, yeah, so we also want to write down the presentation for K1, K2 and K. So let me just do that. Let me just copy paste and just, so I'm going to write generators for K1 as Bij, but nothing else changes. So here's B. Oh, I guess the other thing that changes is here we have T2 and K2 and K2. And then for K, so this is for K2. And then for K, let me call these G's. Guess I can get away without erasing. And then, okay, so this is when it's in K and T. All right, let me, okay, now comes time to just compare these descriptions. So let me make space so we can have them all on the screen and also write some more. Oh, come on. All right, so now what you, well, okay, so first thing, so first thing that I want to observe, so I claim we're basically done with the theorem. We just have to stare at these presentations long enough and see that, so we're trying to say that, so we're trying to describe, we're trying to show this isomorphism. So we have a presentation for these groups and we want to say that they differ by adding these relations. Okay, so the first observation is, well, these GIJs are the union of AIJs and BIJs. Just because every edge in K is either in K1 or K2. And well, yeah, maybe I won't. Well, okay, but this is not a disjoint union. It's not necessarily a disjoint union. I mean, there might be some edges in K that are in K1 and K2. So so to get, well, yeah, so, right, so let's compare. let's compare the presentation for EK1 star EK2 and EK. So all right, so first, the presentation for the free product, remember how this works. We just, well, for the free product of these two, we just put all the generators together. I guess the, okay, at the risk of making a huge mess, I'm just gonna do this. So for the free product, we get this group. So you just combine the generators and combine the relations to get one massive presentation. And well, what you see here, so now you just want to, now we just want to compare this to the presentation here. So the relations, so the generators, there are possibly more generators between AIs and BIs, or I mean, there's more generators with the AIJ and the BIJs than the GIJs because there might be some repetition from things that are both in this AIJ collection and BIJ collection. Those are just edges that are in both K1 and K2. But the relations, all of the relations here, every edge in T appears either in T1 or T2. So that relation, this relation appears on this list or this list. And similarly, every triangle in K is either a triangle in K1 or K2. So this relation also appears on this list. So the only issue is that might be some repetition, but repetition coming from edges in K1 and K2 that edges in K that are in K1 and K2. So let me just say it this way. So to get from presentation, okay, sorry, I'm going to write this on a new slide. So to get from the presentation for the free product to the presentation for the whole edge group of K, we need only add relations that say Aij is Bij if Vj is in K1 intersect K2. That's an edge in both K1 and K2, because that gives us some repetition here. Okay, but that's exactly what Van Kampen is saying. Okay, yeah, so I mean, this isn't particularly deep. I think if I were to try to explain more, it would just be potentially more confusing. So let me stop the proof. This is the heart of it, and well, you can ask questions at some point if you have them. All right, so now I want to talk about something else. So more simplicial approximation. So let me recall what was discussed last time. So a map, and let me call it S, from simplicial complexes is simplicial if it sends simplices to simplices linearly. So last time we explained why such a map is just determined by what it does on vertices. Okay, so this was one of the definitions. And for X in the geometric realization of some simplicial complex, the carrier of X which let me write as car X, is the unique simplex sigma of K, so that X is in the interior of the geometric realization of sigma. Okay, and then the last definition from last time that I just want to remind you of is if we have two maps from between simplicial complexes or geometric realizations, and S is simplicial, then we say S is a simplicial approximation of F if S of X is in the carrier of F of X for all X. X in. Okay. So the main thing I want to do now is, so what I want to do now is give you some more examples illustrating this simplicial approximation definition. So example, so let's start with K, the simplicial complex with two vertices and one edge like this. And let's take F from K, the geometric, so from the interval to itself, the function F of X is X squared. So then S of X is X. The identity function is a simplicial approximation. So let me let you check this. I mean, first of all, S is a simplicial map. It sends simplices to simplices. It sends 0 to 0, 1 to 1, and then it sends the interval 0, 1 to the interval 0, 1. And it does so in a linear fashion because the identity function here, that's linear. And then, I mean, this simplicial approximation criterion, there's really not much to check. I mean, for any point X in the interior, you choose some X like this, X squared is wherever it is. The carrier of X squared is is this full interval. And so the simplicial approximation just insists that S of x belongs inside of there. And indeed, I mean, x and x squared are both in, x is in the carrier of x squared because the carrier of x squared is a full interval. So it's not so interesting. So a more interesting example is to see what can go wrong. So let's take K and L, they're both going to have geometric realization, the interval again, but now I'm going to give a different simplicial structure. So K is going to have, they're both going to have 3 vertices. For K, 0, 1/3, and 1. And for L, 0, 2/3, and 1. And let's take, again, f of x is x squared on the interval 0, 1. And let's think about what properties a simplicial approximation have to have. And okay, well, let me first just say, we're going to see that there is no simplicial approximation for this map. So yeah, so given a function, you can ask, is there a simplicial approximation, a simplicial map which satisfies these properties? And what I'm going to show you here is that for this function and these simplicial complexes, there is no simplicial approximation. And the way we're going to do that is to start just by thinking about what properties S has to have, and see that there's some contradiction. Okay, so first, S has to send simplices to simplices. And it has to do so in a way, if F sends so let me just point out that if F of X is a vertex of L, then S of X is F of X. Since the carrier of a vertex is just that vertex. So this condition just forces S of X to be F of X. So this implies that S of 0 is 0, S of 1 is 1, but then also that S of root 2/3 is 2/3, since root 2/3 maps to 2/3, which is a vertex. So, okay. All right. So now we also know S is simplicial. So S of 1/3 has to be a vertex. So there's 3 options. It could be 0, 2/3, or 1, but since it's a simplicial approximation, S of 1/3 has to be in the carrier of F of 1/3, which is, so F of 1/3 is 1/9, and the carrier of 1/9 over here, so 1/9 somewhere here, is the interval 0 to 2/3. So this means that S of 1/3 is either 0 or it's 2/3. It's one of the vertices, since yeah, S of 1/3 has to be a vertex of L. Of L. All right. Okay, so now let's consider cases. So in the first case, let's suppose S of 1/3 is 0. So then, well, so if S of 1/3 is 0, then on this whole interval, the map is 0, because 0 maps to 0, 1/3 maps to 0, and it's supposed to be linear on this interval. So then, but now let's think about what happens on the interval 1/3 to 1. Well, it maps this interval, 1/3 maps to 0, 1 maps to 1, so it maps this to the interval 0 to 1. And it does so in a linear way, so we can write down a formula for it. The linear map that sends this interval to that one is exactly, let me just look at my notes. So 3/2 x minus 1/2. Yeah, so that sends 1/3 to 0 and 1 to 1. But then this implies that S of √2/3, well, you plug in √2/3 to this formula and you don't get 2/3. I mean, in particular, √2/3 is irrational and the coefficients here are rational. So there's no way this could be a rational number. But anyway, you could also just evaluate, I guess. Okay, so that doesn't work because we said S of √2/3 should be 2/3. And similarly, if S of 1/3 is 2/3, you find a contradiction in the same way. So from this, we conclude that F does not have a simplicial approximation. Okay, so the main takeaway at this point is, so there's this definition of a simplicial approximation. It's not so intuitive what this is capturing. It's a technical assumption, or it's a technical criterion. And we've shown that not every function has a simplicial approximation. So now let me give you a lemma which motivates this definition. Why do we care about simplicial approximations? So if S is a simplicial approximation of F, then F is homotopic to S. So if F has a simplicial approximation, then F is homotopic to a simplicial map. Okay, so, and this is going to be useful for the edge group theorem. But for now, let me just explain the proof of this. So we want to show F and S are homotopic. So we want to show there exists a homotopy, which is a function like this, so that if you restrict to k times 0, this is F, and if you restrict to k times 1, this is S. Right, so first recall that K and L are subsets of Euclidean space, we could think of them as subsets of some common large dimensional Euclidean space. And so the obvious thing to try is the straight line homotopy. So let's consider h xt to be 1 minus t times f of x plus t times s of x. Now, what we need to do, so we need to check that h of xt is in L for all x and t. So if that's true, then this works. I mean, the criterion, yeah, we just need this map to have image in the geometric realization of L. Right, so for x in the geometric realization of K, and well, we have that, so let's let sigma be the carrier of f of x. So we know that s of x is in the geometric realization of sigma. So the picture is like this. So here's sigma. This is in L, and f of x is like this, and well, s of x is somewhere. It could be like here, it could be here, it could be on a vertex, but it's somewhere in the geometric realization of sigma. So let me just pick one of those. Let's say it's here. And well, the geometric realization of sigma is convex. So the straight line from f of x to s of x is contained in the geometric realization of sigma. So, and that's exactly what we need, or that gives us what we want. So that this homotopy, the straight line homotopy, just moves f of x to s of x along the straight line, but that straight line is contained in the geometric realization of sigma, and hence also in L. Okay, so that's the proof. Okay, so we like it when a map has a geometric realization, because then that map is homotopic to a simplicial map, which we'll see is a useful thing. But we've seen that not every map has a simplicial approximation. But there is some good news, which is that, well, okay, let me just state it as this theorem, which we'll discuss more next time. This is called simplicial approximation theorem. And it says if F is any map between simplicial complexes, then there exists a subdivision K prime of K, so that I'll say what subdivision means in a second. If you think about this map as a map from the geometric realization of K prime to L, this map has a simplicial approximation. So here, a subdivision, so let me just draw a picture for what subdivision is going to look like. So it's a process that you do to simplices, to each simplex of a simplicial complex. So say you start with this two-dimensional simplex. If subdivision of it is going to be this way of splitting it into smaller triangles. You start with a triangle, you split it into smaller triangles. Subdivision is going to have the property that it doesn't change the geometric realization. So you replace this simplicial complex with another simplicial complex where the triangles are smaller, and you don't change the geometric realization. So F also gives a map from the geometric realization of this new simplicial complex, because it's the same. And the claim is, well, once you make these simplices small enough, once you subdivide small enough, then there is a simplicial approximation. Okay. So we'll talk about this more. We'll talk about this more next time and see how to use it in practice.